Okay, let's look at a more complex visual pattern now. Because unlike the previous ones, now you're going to have to look at side lengths that are different. So this is actually going to matter for the equation that we create. We still want to say let x be the pattern or size number, just because this diagram calls them size. And then let y be the number of blocks. So here's what you should hopefully immediately recognize in this pattern. So when I looked at this, the first thing that I noticed was that no matter what image we were looking at, there was always one block that kind of stuck down on its own, and then one block that kind of stuck up on its own in each of these visual patterns. So this means that something is consistent from step to step. No matter what is in here, we're going to be adding 2 blocks each time. So that's something to kind of keep in mind as we actually create our equation. We're going to be adding 2 once we figure out the actual, the end piece of that. The other thing that we're going to have to remember here is that, again, we want an equation that relates the size or the pattern number to the number of blocks that are in the actual pattern. So here x will be 1, here x will be 2, here x will be 3. Let's just make a nice table of values to give ourselves another way to represent that, because once you do this, you might also find it's easier for you to see the patterns too. So when x is 1, y is going to be 5. There's 5 blocks. How many do we have here? 2 and 10, and then 3 and 17. Alright, so just like in previous visual patterns, we had to kind of start looking at these as an area. Once you identify something that's constant in each of the patterns, which in this case was the block being added on top and the block being added on the bottom as well, you'll probably notice here that we have you have some kind of a side length there and some kind of one there too. And just like it's the same here, we have some blocks there and some blocks here, some here, and then some here. If I were looking at what the visual pattern was showing me, I would start off by just actually listing the lengths and widths of these rectangles in the middle. So here I have 1, and then there we have 3, and then 2 we have some kind of width of 2, and then a length of 4, and then here it's 3, and then there it's 5. So then something that should emerge right away is that one of the side lengths in the rectangle equals the pattern number. So here's 1 and there's 1, 2 and 2, 3 and 3. So that's something. So that makes me think that if we're looking in terms of an area of just the middle rectangle, this is not the actual full equation yet, the area of just the middle rectangle. So one of the things is going to be x, like one of the side lengths is x, because 1, 1, 2, 2, 3, and 3. I'm pretty convinced of that just by that point. So I think that one of the side lengths is going to be x. And then the other thing to do here is maybe let's try and see if there's a way that we can relate the other side length to the pattern number. So how can we relate the number 1 to the number 3? Well, I would ask myself, how could I relate that? And I would think, well, if you add 2 to 1, then you're going to get 3. So like that would be 1 plus 2, which is like saying x plus 2. So I wonder if that also applies to the other ones. So how could we relate 2 to 4? Well, if you add 2 to that, then you're going to get 4. So that's like saying x plus 2. Alright, so 2 in a row are following the same pattern, but now we need to do the third one just to verify. Give ourselves the additional evidence. So if you add 2 to 3, then you'll get 5. So that's also like saying x plus 2. So that means that this side length, this part of the rectangle, like the width, that's x. And then the other, in each case, we saw that it was x plus 2. So that means that this middle area, or the area of these rectangles for each pattern, are equal to x times x plus 2. So then in terms of creating an equation, I think we're pretty well there, because we know what's the equation that represents the area of these kind of middle rectangles. So we know that that's going to be x times x plus 2. And then in each pattern, we also have one block added on top and then one block added to the bottom. So that would be plus 2. And in terms of how we're getting that, we're getting the blocks that I shaded in green. That gives us the plus 2. And then the areas of the rectangles in the middle, that's how we get the x times x plus 2. So this there would be our equation. Y equals x times x plus 2 plus 2. And then let's just try and expand and simplify this. So since we're looking at a complex example, if you want to aim for that level 4, you're going to need to have a fully expanded and simplified equation. So if we have y equals x times x plus 2 plus 2, again, distributive property, that's like saying x times x plus x times 2 plus 2. So then what do we get? X times x is x squared. X times 2 is 2x plus 2. And then that would be our completed, expanded, and simplified equation. And then you could always just go back and double check that it actually worked. So if x was 1, that would be 1 plus 2 times 1 plus 2. Does that give us 5? Yes, it does. What if it's 2? We have, so 4, because 2 squared is 4, plus 2 times 2, that's 4 again, so that's 8, plus 10, that would be 10, plus 2 is 10. Do we have 10? Yes, we do. So we also have verified. I didn't do a formal verification, I just kind of did it like out loud, but that's also a way that you can verify that the equation's right. If you sub in 1, 2, and 3 and you get the number of blocks from the actual pattern and you count it, you would know that you did it correctly. So this would be an example of a more challenging pattern, like heading towards like more level 4 territory. So study this example really, really well if that's the level you're hoping to achieve at for the visual patterns and graphing the quadratics.